And basically, the game plan is going to be, let's take all that good transformer architecture stuff that we learned about the last few times, and let's start modifying it to build various kinds of language models. And specifically today, we're actually going to do foundation models. But first, we're going to start off with where we left off last time. And also some announcements. I'm going to release the first homework assignment today. It is new, so if there's anything wrong with it or you spot some weird things, just let us know. It's going to be due, I think, in a week and a half or 2 weeks, but it's not super complex. The main idea is it's going to ask you to do a bunch of parameter counting for these models that we've been talking about. So we're going to talk about GPT-2 later today. It's going to say, hey, go through all the layers, look at all those pieces of parameters, the trainable parts that we've been talking about. How many are there? Then go in PyTorch and conform it. So just to get your experience and make sure that you understand concretely what's going on, which is stuff that we've talked about at a much higher level. OK, so in terms of where we are, we'll do some stuff about models today. I am guessing we won't finish, so we have the next lecture on Tuesday where we'll probably finish up. Basically, we're going to talk about what happens if I build models that only have encoders, or if I build models that only have decoders. That might sound weird, but that's actually going to be something very useful for us. Afterwards, next week, we'll talk about prompting. It won't just be, write something and let the model finish it. We'll talk about some more formal techniques. We'll get into specialization, which is going to get very interesting. What if I want to fine-tune my foundation model efficiently? And then finally, coming up in 2 weeks, we'll talk about alignment. This will be also a form of specialization, but the goal is going to be, can we make the model behave in a way that we actually like and want? All right, so for today, we'll finish up SSMs from last time. We only had a few minutes at the end of the lecture to talk about it. We'll start talking about encoder-only models. So we'll kind of go back to our transformer architecture. We won't talk about SSMs too much more. And then we'll go ahead and start talking about, well, what can we do if we want to make this thing into a really powerful form of embedder? And that's going to give us this architecture called BERT, which is really the first foundation model that is worth really talking about. And then afterwards, at the very end, we'll start talking about decoder-only models. It's going to turn out that basically every large language model that you use is really a decoder-only model. We're going to take our transformer architecture, take off the first half, and then train it on a lot of data. And that will produce for us things like ChatGPT, which is pretty interesting. All right, so let's jump in from last time. We got to this equation, right? And it looked a lot like an RNN. You can safely ignore those bars over the different letters. In fact, we're not going to even get into details. Let's ignore the exact shapes of these matrices and vectors. All we're saying in this equation is that we have two things. We have, or three things, let's say. We have an input. We get that input at each time step, U1, U2, U3, and so forth. We have an output that we produce at each time step as well. That's this Y, Y1, Y2, and so forth. And then we're going to have a state where we keep track of what's going on. The state is just this X. And there's also a state at each time step. Now, how does the state evolve? It changes over time based on the previous state and also based on the current input. Everybody comfortable with that? Now, even if there was no input at all, the state would also evolve, but it would evolve in a very simple way, right? The fact that we have this input that we don't know what it is what causes the state to change in a more interesting way. So here it is. The entire equation that tracks these evolutions is just the top one. That's the state update equation. xk is given by a times xk minus 1, the previous state, plus b times uk, the current input. As for the output, it's the simplest thing that we can do. We're just going to say it's a direct function of the current state. So yk is c times xk. OK, so very simple equation, relatively little going on. We used to have a d, which is like a direct influence on the output from the input. We got rid of it. We can do things like approximate these continuous time evolution equations with different ways of discretization. We're going to kind of ignore this. We now have a very simple RNN. Let's try to look at it and understand it. And let's see if there's any interesting connections to deep learning that we can make. And to do this, we did this really weird thing where we started writing down this equation for time steps like k equals 0, k equals 1, k equals 2, and so forth. So let's see what happens when we write that stuff down. Here's the very first version. The very first state is just given by the input that we get, right? There's no previous state before x0. There is no such thing as x negative 1. So nothing happens yet. my first state is my input, b times u0. And then my first output is just c times x0, which if I plug in the formula for x0 is c times b times u0. All right, everybody OK with that? OK, now let's do the same thing, but let's go one step further into the future. Let's go to x1. Well, I know what x1 is. It's a function of the previous state x0 and the current input u1. Let's go ahead and plug in that previous state. I get this equation, ab u0 plus b u1. That sound good? Again, no work, just algebra, plug and chug. And then, of course, y1 is just c times x1. So I take what I have in x1, put a c on the left in both terms. That's it. OK, let's play the game again. Same deal. x2 is taking x1, left multiplying by a, and then adding in b times the current input, u2. Still plug and chug, no work. And then y2 is exactly the same thing, except I multiply x2 by c's on every term. All right, everybody comfortable with this? Again, no actual intellectual work. All I've done here is rather than write down each equation based on the state, I am now plugging in the full formula for the state that only involves inputs. Everybody see what I mean by that? If you see these equations for x2 and y2, notice that the only thing playing a role in them is the inputs, right? Of course, they depend on the previous state, but that previous state is itself a function of prior inputs. Sound good? OK, so it looks like we can actually maybe even skip all this business about x and just look at the output y. The output y is some complex-looking function of all the inputs. So y2 is a function of u2, u1, u0. yk, more generally, is a function of uk minus 1 all the way back to u0. And in fact, we can write down what the function looks like because it's not too complicated. It's going to have this form. The only thing that's really happening, basically, is when we say, hey, what happens to the input when I'm considering it as part of the current output, well, that a in the middle, that term, is raised to a higher power because we're constantly evolving it. What is that higher power? It's just a number of steps that have passed since then. So for yk, the first term that has a u0 is going to have an ak. For u1, it's going to have an a to the k minus 1, and so forth. This is just an algebra pattern, right? Nothing really has happened here either. OK, cool. So now we know a way of expressing the output directly as a function of the input. It's just based on these c, a, and b. These are conveniently things that we're going to train, these matrices. But if you kind of look at it, the interesting thing about it is that it really is a convolution. So I'm writing this in the following way. I'm no longer talking about one output, yk. I'm talking about the entire sequence of outputs, y1, y2, y3, and so forth. And that entire sequence, that whole vector, is the convolution of a particular sequence that we'll talk about. I'm going to call it k. The convolution of that with u, which is the entire sequence of inputs. OK, notationally, does that make sense? Cool. So again, a convolution here is a 1D convolution. You're probably more comfortable, in ML at least, with the 2D version for images. Here is just over a sequence of some length and nothing else. This is actually how it's done in EE typically before you do higher dimensional versions. Let's see what the two sequences look like, right? So the top one is this k. And what does it look like? Well, it starts off by being CB, then CAB, then CA squared B, and so forth. The bottom one is just our input sequence. OK, how can you tell that this is what's going on? Well, just do the standard definition of convolution. Take one sequence, start shifting it over the other, compute your dot product, shift it over one more, compute your dot product, and so on. What do I mean? Like, literally take this input sequence over here. You say, OK, take u0, put it over this CB. That gives you your y1. Go ahead, shift it over by 1. You do u1 times CB plus u0 times CAB, right? That's your next y, and so forth. All right, so convince yourself that literally manually performing this convolution between these two sequences is giving us exactly the outputs that we're looking for. In other words, the output sequence is the convolution of two fixed sequences. One is the input sequence. The other is a sequence that depends on all of these matrices that happen to be our parameters. All right, everybody OK with this? Anybody confused? OK, so why do we care about this? That's a good question. Well, we kind of started off motivating this whole section by saying that these architectures are subquadratic, right? So somehow this should relate to complexity when we will actually compute this output sequence. Now, one problem is, at least so far, when I told you things like shift the sequence over, compute the output sequence, it's not really cheaper, right? And here's what I mean by that. I have to compute every y, right? How many y's are there? That's the length of the sequence, length L or T or N or whatever value we want to use. And for each of those outputs, I have to do a full dot product, right, between the two sequences where I have them. And again, that's a thing that's of length L. So at least naively, computing this convolution is still like an L times L thing, which is exactly the same cost that we were getting for doing self-attention. So just pointing to this convolution and computing it naively hasn't saved us anything yet, right? Previously, we did self-attention, which had a different form, but it was quadratic. And naive convolution here, with this R and N form, is also quadratic. But let's see if we can be smarter about some things. OK. Now, why are we paying so much for this convolution? Why is it length L squared? When you go back to CNNs, you're not paying that huge cost, and that's one of the advantages of CNNs. Well, the reason is this is a very long filter, right? Like, the length of this filter is really the length of the entire input sequence. And normally, that's not what happens. In a typical CNN, your filter is much smaller than the input image. Everybody agree? Like, if I'm doing ImageNet and my images are 227 by 227 or whatever, well, a common filter size is 5 by 5. It is much, much, much smaller than the entire image. And if I told you, hey, you should have a filter that's also 227 by 227, you would say, yeah, but that destroys the advantage of CNNs, right? I now have something equal size. I have to move that whole thing over. It's going to be extremely expensive. So let's see if we can get slightly more clever about this long convolution. And let's see if there's something we can do with it. Right? Let's try something slightly more clever that we learned back in Signals and Systems class, which may have been a while ago. It certainly was for me. OK, so back then, you learned about something called, assuming you've taken these classes, kind of the time domain and the frequency domain. And hopefully, someone recalls some of this stuff. And one thing that was very interesting about time domain and frequency domain is that you can transform between the two of them and transform back. And certain operations have analogs from one of those domains to the other that are simpler. And specifically, a convolution in the time domain is just a basic element-wise multiplication in the frequency domain. So rather than doing this convolution and shifting the sequence over and each time computing a full dot product, if I move my sequences to the frequency domain, all I have to do is multiply their elements. There's no shifting anything. All right, so hopefully some of that's familiar to some of you folks. For those who are new to this, it's actually one of the most beautiful results. But let's go ahead and see how we can use that. OK, so if it is true that I could shift my sequences to the frequency domain and perform this element-wise multiplication, that would be great, right? Because if my sequences are of length L and I do element-wise multiplication, the cost is O of L. That's linear, not quadratic. We're in good shape. But there is a slight problem, right? We do have to shift our sequences into the frequency domain. We have to transform them. And of course, that transformation comes at some computational cost itself. And of course, we have to pay it twice, right? Because we have to go into frequency domain and then come back out of it, transform ourselves back. So we need an algorithm that can do this transform that is not as expensive as L squared, as the quadratic term that we try to avoid. Very conveniently, people 75 years ago discovered that you could do that. You can do it with something called the fast Fourier transform. Interestingly, even though formalizing it took till the 40s and 50s, people all the way back to Gauss actually kind of knew about this trick. So the fast Fourier transform has a much faster computational complexity compared to these naive quadratic things. It's L log L. And the inverse version that takes you back from frequency domain to time domain is also L log L. So here's the game we're going to take. Rather than naively computing this convolution that gives me the output in an SSM, and that naive computation in time domain is L squared, which saves us nothing compared to attention, we're going to do this trick. Let's first pay a cost of L log L to move to frequency domain. Let's perform the convolution there. That gives me my output sequence. That costs O of L, so that's not even important. And let's transform back using inverse FFT. And if I do that, again, it's another L log L. So the total is still L log L. In other words, we are subquadratic, which is the thing that we were trying to do. So that's the basic story here. We can actually compute this output sequence Y fast. despite the fact that I have two sequences that are of length L, despite the fact that if I do things naively without any transforms, I still pay a quadratic complexity term. OK, any questions about this? It is somewhat magical. Cool, so all I've really told you about here is that when you want to do training, instead of paying the cost of attention, you run this whole thing in this special convolutional mode and use a fast algorithm to be able to do a forward pass, for example. So this is something very beneficial. And why do we really care about this? Our original motivation was, well, we want to handle very long sequences. We could not do that with a transformer because we have to pay the square cost. Here we can because L log L is very small compared to L squared, even for very long sequences. So 1 million times log of a million is not that big, whereas 1 million squared is quite large. That's the basic story and motivation for SSMs. Now, in practice, there's a lot of actual details that have to get taken care of. Just showing you this formula is not really enough. All we're really doing in the most basic formulation is saying, yeah, these things are going to become trainable parameters. Unfortunately, if that's all you do is instantiate them as parameters in PyTorch and go train a model, it actually will not work very well. It took a long time to kind of figure out exactly how to make these things work. And sort of the first paper that did it in a good form is this paper called S4. So this is what we were talking about. This is a paper coming from some folks that I'm also friends with. Read this paper. It's one of the best ones in the last 5 years, frankly. But you can see how much kind of mathematical work it took. It turned out that for A, right, this transition matrix, you can't just parameterize it to be anything you like, and you can't initialize it to be anything you like. There are special things that you have to do to make this whole thing work and make training stable. And these special things really depend on some very beautiful math that we're unfortunately not going to have time to get into. OK, so we have this interesting kind of nice model now. We have a fast way of computing outputs. We did some special magic and some tricks to make these things actually capable of learning. From these basic parts, you can actually start defining layers. Just like how when we talked about attention last week, we also spent a bunch of time defining the base operation and then saying, here's how we're going to build a layer out of this. And that's almost exactly what you've seen. You kind of define a layer, stack a bunch of these different things together, very similar to multi-headed attention. You mix them with some linear layers. You place some activation functions at the end. Again, nothing special, exactly what you do for a CNN. And then you can create a large model based on this. You can size it up to whatever you want. OK, now let's talk about some good things and some bad things from doing this, because it's going to turn out that just doing this itself is not going to be enough for language modeling. OK, so S4, this model based on the principles we just talked about, because of this L log L complexity, you can handle very long sequences. So here's an example from the paper. There is this really interesting benchmark called the long range arena. And the basic idea is that it tests your model's ability to handle very long sequences. OK, so one example of such a sequence was something that had length about 16,000. At the time, any transformer-based model would choke on something this long. But this S4 model was basically able to get almost perfect accuracy, again, using the fact that you can handle very long sequences. However, there is a downside that you can actually slightly guess. The downside is that you can't easily handle something that are called selective tasks. And let's see one quick example of this. So here's a non-selective task. We're going to distinguish it from a selective task in just a second. Here is all we're trying to do. We want the input, which has some objects of interest. There are these things on the left in color, blue, orange, red, and green. We want to have these things be copied in the slots that we've defined over here. OK, I'm defining this stuff in a cartoon sense, but of course you could implement a task like this. It's literally take the sequence from the beginning of some length and put it somewhere at the output in some positions that I've defined beforehand. Right, so again, I want to move that input into this black area, and you can see the output that just says, OK, indeed, I pushed things where they should be. OK, now I said that we're doing convolutions, right? That's basically what's going on here. What I'm going to do is convolve the input with some sequence to produce the output. That was our whole story so far for how these SSMs work. Well, in that case, I need to be able to get something that's going to fit this convolution, this filter sequence, that can take that input and produce that output. And indeed, that's what you're seeing over here. This thing on the bottom I'm putting in some spikes, I'm putting in some ones in the positions I want to copy, and in the places where I want to copy them to. And certainly I can solve the problem, right? I can fix this sequence, this is the solution over here, and I can force it to produce the correct output. Now, this thing would also work if those colors were different, right? I can design a filter sequence that copies something from a fixed set of positions to a different fixed set of positions. The same convolutional sequence, the same filter will always work for these, no matter what the inputs are. All right, everybody comfortable with this so far? If anybody's lost, this is also a good time to ask. OK, everybody's happy. OK, let's see what happens if I make the task slightly harder. Let's suppose that rather than saying, hey, there are particular fixed positions that I want to copy from, I say, no, I will also, at the input, define which those positions are. So it's no longer a task where I always want to copy what's in the first 4 components of my input. It's a task where I'll define, when I produce the input, also which are the positions I care about. And notice that they're no longer first 4. In this particular input, they're the 2nd, the 5th, the 6th, and so on. All right, everybody OK with that? Go for it.
So like an example that we can see in the real world is if we're using something like an LLM to summarize a paper, we wanted to pull out the most important sentences from the top 4 most
right.
important sentences.
Yeah, and that's a good example. Yeah. Now, of course, this is a very toy example. It's an abstraction. But you're right. That's exactly where it play a role. OK, so we call this thing selective copying because we're not copying a fixed component of a sequence. We're saying you should copy certain selected elements. And these are not known beforehand. They're given in the input. Well, the problem here is you can certainly try to design a filter. But this filter is fixed, right? This is the thing that we trained in our training data. Right? This is not something that we can change at test time depending on what elements we wanted to pick. It's fixed. And in fact, you can, for this exact fixed input, design one. But then the next input may say, hey, actually, you should have copied some different positions, and you're stuck. Everybody see what I mean? So this fixed kernel approach, it really cannot work here, at least for this selective copying task. And indeed, the selective copying task is something we really want our language models to be able to do. All right, so the solution is going to be going beyond this kind of S4 model that I've talked about into some other models that still have these SSM principles, but can do this kind of selection. In other words, they can do something more data dependent than before. OK, and this is the kind of intuition behind a very popular model. This is probably the most popular of these SSM models that are used today. It's called Mamba, because it's fast, and Mamba is a fast snake. Anyway, kind of lame. So you should read this paper. It's quite interesting. The only part I'll pull out here is just a very quick look at the 2 algorithms that we've talked about. On the left is just the simple design for an SSM. If you look at it, it's exactly what we said. You're computing the SSM operation. The only things we're really doing is defining, hey, what are the parameters and what sizes do they have? But notice they're exactly the ones we talked about, the A, the B, the C. There's some slight details about the discretization that we haven't talked about, but otherwise you should recognize what's going on here. And notice that when we go compute the output, we have the 2 ways of computing it that we talked about. Right? We have the recurrent way of computing it, and we have this convolutional way of computing it that we spent a little bit of time developing. But this thing does not have this capability of doing selective copying. So we need to make some modifications to it. And that's exactly what's happening over here. So notice that rather than saying, hey, B is just a parameter, C is just a parameter, we are now going to start them off with something that is data dependent. And I'm not going to tell you exactly what that is, but you should read the paper. This SB of x and SC of x, notice that these guys have dependency on the input x. And this is the trick that makes it possible to actually handle these input-dependent things like selective copying. Now, the operations for SB and SC turn out to be very simple, but they do use the x, and that's the thing that matters. Now, one thing that's very annoying is that by doing this, we actually break the convolutional form. Right? We no longer have a linear time invariant system, which was the thing that permitted us to do FFT. Fortunately, there's ways out of that as well. So for example, this scan approach is actually also fast, in the same way that FFT was. So basically, we can get the best of both worlds. We can still be efficient. That efficiency still lets us work with very long sequences. But additionally, we can handle things like selective copying as well. And all of this can be done with just a tiny bit more complexity than the basic SSM algorithm. OK, that's as far as I'll go for this stuff. We really could spend like 2 free lectures on all the different things people have proposed. I encourage everyone to kind of check out some of the interesting papers. There are other sort of competing formulations of this. So linear attention is a good example. There's actually a ton of these. People have been trying to resurrect RNNs more broadly ever since transformers took off. This is actually also a really good source of potential papers that you guys should go read and present on. All right, next we'll be getting back to transformers. Any questions about this whole thing? Go for it.
So with all the SSMs, we assume that the current state will depend only on the previous state, right?
Yep.
And that was
Yep.
RNN initially.
Yep.
But the transformer came because we also wanted to attend with first
Yep.
word, which can get into last word, which
That's
is
right.
in the future state. So how we are comparing this attention with all the SSMs?
Through the results, basically, right? We have 2 different mechanisms. It's not a priori clear which one's inherently right or wrong. The question is, which one can be used to build a good language model, or something else that we want to build with these? For a long time, people thought, hey, attention is necessary, right? If you build anything based on recurrent principles, you'll lose too much somehow to be good. What these new models are showing is that may not be true, right? And of course, in the end, when you talk about models of equivalent sizes, right, you only have so much capacity to store information, whether that's through attention or whether that's through some state matrix. Either way, though, right? So the only question is, what do you do with it? What is the actual parametric form of the operations? And how well can you train them? And these things will govern what the results look like.
But before this, when RNN was proposed, like they only had a non-linear function over it, and it made
Yep.
it only linear.
Yep.
So how does
These are also nonlinear, by the way. We are going to add nonlinearities to things like our Mamba layers or SS4 layers too. So they actually won't be that different. The problem for basic recurrent models is whatever we do with them, they tend to forget important information. That is not the case for these SSMs, which is what makes them viable for language models. But the principles are indeed the same, right? That's why people care so much about recreating RNNs. And they are very convenient to use. Yeah?
Size state is a problem for the longer in the SSM.
Say that one more time.
So there's a fixed size of
Yep.
the state, right, where we represent the vector dimension.
It is a problem. You can forget stuff. If you have too much information, you'll always have to forget stuff. The big question for all models, whether they're attention-based, recurrent-based, or anything else is, how do you compress information, right? And if you compress in a way that the salient stuff does not get forgotten, you'll win. If you forget stuff that matters, you'll lose, right? But either way, you face this exact same problem. Cool. Everyone's asking great questions. I encourage you guys to keep going with those. Let's go back to transformers for a second. And again, we've now seen this picture tons of times. We all feel comfortable with it, hopefully, at this stage. If you don't, the homework assignment will also kind of force you to go through and make sense of every part of it anyway. OK, so let's kind of get back to our encoder-decoder models, because this is what will inspire the next part. We basically had this sort of natural thinking that, well, we're going to do translation. And therefore, first, let's encode the sequence from one language. And then let's decode it into a different language, right? And I have more pictures for what the intuition should look like. They're kind of silly, so don't take them too seriously. I want to start with the book on the left in one language. I want to move to the book on the right in a different language. I want to go into some abstract latent space first, right? And this latent space will represent whatever's going on in the passage from the book. But it won't be based on language, right? It'll get rid of those unimportant things. And then when we decode, we'll actually insert those back in, but in the new language we're translating to. So this is the way to think about these things. We're shifting into this latent space. We'll do stuff there, and then we'll decode back into whatever we want to. And indeed, that's kind of what we saw, right? We had this idea of, fine, we're going to encode stuff until we get to the latent space, and then decode what came out of it. And we're always going to keep track, at least, of some of what the encoder produced, because we pump it into the cross-attention parts. OK, so we talked about all of this stuff last time. We saw the examples of the encoder. The block in the encoder was simple. It was just self-attention plus our MLPs. And then we said, OK, for the decoder, the only thing that's different is we still do self-attention, but we're going to also do this cross-attention that takes stuff from the encoder and the decoder. And then finally, we'll still have our MLP. So hopefully, everyone's feeling comfortable with this. We saw all these examples of the what's really going on in here, although it's still pretty high level. And we discussed, OK, well, if we're actually going to design it, let's make sure that we add in all the deep learning tricks. So for example, skip connections and normalization. OK, same deal with the decoder. We talked about it, and we said, hey, the only special thing that's going on is this encoder-decoder cross-attention, blah, blah, blah. Everyone's hopefully feeling very comfortable with this stuff at this stage. Anybody found out that they were confused since we talked about it last? No, we're good. OK, cool. So cross-attention, again, another analogy that you shouldn't take too seriously either is kind of think about starting in the original space of raw input language and summarizing the important key things, right? Like you might take notes after you read a book. And you might take these notes and compress them into something else and compress them further and so forth until you get really the pure abstract meaning of what's going on in that book passage. That's the stuff in red over there. And then we start decoding it, right, until eventually we get to the other language. I should have put these pictures in kind of our slides from last time, but yeah. This is just for intuition. Don't feel like they're too important either. And notice that these sort of most abstract key term things that came from the encoder layer, we're always pumping into everywhere, right? We're always keeping track of those so that we don't forget them. OK, we did that. And the last bit that we also kind of talked about last time, which was interesting, was the fact that even though our decoder is going to be producing a sequence that might be long, we haven't yet generated the future tokens when we're currently generating one of them. So we can't do attention over them. So we have to mask those out. And all these things together are basically all of the things that make a standard transformer work. We also discussed how do you actually go ahead and finally predict a word. And from this, we had this full architecture. This is the full picture that we saw last time. OK, and then we said a little bit last time about training as well. The training was pretty simple, right? We just said, hey, there's some standard translation data sets we can go ahead and train on. For example, pairs of sentences where the input's in English, the output's in German. We just trained this guy. We have a bunch of training data, 5 million pairs. And we optimize using something like Atom, very standard optimizer for deep learning. OK, so I breezed through that. But this is all the stuff that we talked about for the last week. So hopefully, everybody's good. OK, then from this, we're actually ready to proceed to what should we do next in terms of building things that are not translation models, and they're not specific to that task, but can be used for a wide variety of tasks instead. OK, let's take our 2-minute break. Does anyone have questions? And if not, feel free to hang out. And then we'll start talking about what happens when we get rid of decoders in just a second. Yeah.
We're not doing, oh, sorry, I think we're not talking about something. So, well, there's a bunch of terms that don't show up because there are link events, right? right? The only time the two things match up perfectly is when you're in the last step, right? So every prior output computation, you do have to check.
Hello.
This architecture.
Yep.
We are doing the masking first.
Yep.
So should that be flipped or like doing like the cross attention first and then the masking next?
So it's an interesting question. Really, you actually could change it. You could switch the order, and probably nothing terribly bad would happen. The only thing that you really want to do is to make sure that you have something to do cross attention on to begin with, right? And one thing that's a little bit annoying is like if you put it first in the very first encoder, you actually have nothing to work on yet, if you see what I mean. Well, we could probably get around that. Like I don't see like an inherent reason not to switch them, other than arbitrary decision.
Just wasn't sure because I saw
Is it an application to something?
yeah, it's like it was built off of like the S4
Yep.
the model architecture,
Yep.
I think. It's like one of those.
Yeah, basically for every domain, someone has a Mamba for that domain.
Yeah.
I'm broadly familiar with the ones for like the areas I work on, like graphs and a bunch of other things. Well, we could talk more because I'm curious how it gets applied to
I'll
every
mention
possibility.
a lot more next week
Okay,
when we meet,
perfect,
so
yeah.
we'll talk.
Does anyone use these linear attention or linear models in practice, or is it just pretty much only deep?
They're starting to be used in practice. So there's two things, right? One is I want to build a general foundation model or language model that's reused for everything. There, you have to invest, right? You have to pump in 20 million to get something of a reasonable size, right? So first, these guys have to convince some company to blow 20 million to validate the idea. That's not trivial, but NVIDIA actually has done it. So it's happening basically there too. The second piece is I want to build a more specialized model for something very particular, and there, yes, right? And the place that people really care about is like really like bioengineering applications where your sequence is DNA, which is very long. And transformer-based models with DNA will die, because I do want to work over 1 million base pairs or whatever. So there are real like victories for these kinds of models.
But all like the chatbots and structural factory models, those are still on the transformer.
The ones you're using now are, but like I said, there is at least one NVIDIA model that is a combination actually of transformers and SSMs, and it's pretty good. So there's a real potential that in 3 years, like when you use the next version of ChatGPT, you might be using something that at least incorporates these, but no guarantees. Yeah.
If we convert it to frequency domain, then it will be helping. Like how is it? Like how?
How do you perform the operation?
Yeah. Like how do we like why is it helping in this case?
So the reason
For it is you want to go to frequency domain because there, the cost of performing convolution is very cheap compared to the cost of doing it in time domain. If you do convolution in time domain, it's elsewhere. If you do it in frequency domain, it's just out. It's literally you take the two sequences that are now in the frequency domain, you multiply their corresponding elements. Literally, that's it. Now, why is that the case? We'll have to do the theory for certain systems. That's a lot harder to solve. So I can recommend the book, for example, and you can see the derivations. They're not super challenging. There is one thing that you have to go through, and that itself is an issue. The issue is that the basic version of the transform also costs you extra. So you get nothing, right? That's what we need as a key. The fast part is the fact that we do that. But basically, yeah, moving it would cost you a lot. Doing it there costs you a lot. Going back costs you a lot. The total is not too bad.
All right, let's go ahead and get started. Let's talk about encoder-only models. We're going to build up this model called BERT. It's called BERT because it's the successor to Elmo, and these are names of Sesame Street characters. We'll talk about its architecture. We will see that this thing is a foundation model, in exactly the sense that we talked about 2 weeks ago. We talked about foundation models as being, 1, self-supervised, 2, being trained on some fake pretext task that is self-supervised, and 3, being fine-tuned for particular tasks. This is actually exactly how it's going to work for BERT. And in fact, even the training itself is going to be multitask. So it's really going to incorporate all the things that we talked about kind of before. Notice that transformers, the actual translation-based model, did not have any of this, right? It was a purely supervised model that we train on pairs of input-output sequences. All right, so we talked about the reason for encoder-decoder when we had kind of 2 logical things that we cared about. One thing that we did is we wanted to have outputs in natural language. It had to be a sequence-to-sequence model where the sequences are tokens, or in other words, words. So one requirement was that the output is a sequence in the language we're translating to. The second requirement, which is why we did this whole encoder-decoder business and why we did cross-attention, is that we wanted the output to be very, very close to the input, literally translated, right? It's the same sentence. Nothing has changed there. So one thing we'll do now is try to think of what could happen if we relax one of these 2 requirements. And the cool thing that's going to happen is that if we relax, let's say, the potential first requirement, which means we're no longer producing sequences, we can build some really, really good embedders. So these will be encoder-only models. We'll get rid of the decoders. We're not going to go ahead and produce a translation or produce any more text at all. So this will not any longer be a sequence-to-sequence model. It'll be a sequence to something, and we'll do different somethings there. The other possibility is going to be getting rid of the encoders in the first place, doing a decoder-only model. And we'll see that if we do that, sure, we're not going to be able to do translation. It'll turn out, actually, yes, we can. We'll be able to build generative models. So this will take us into things like all the GPT family of models. So this is going to be our 2 different paths. Let's get rid of one of those requirements, get encoder-only models. Let's get rid of the other one. We'll get decoder-only models. And these will have different value. One will give us good embeddings that we can do lots of tasks over. The other will give us generative language models, which, as it'll turn out, we'll also be able to do lots of tasks with, but in a different way. Everybody OK with this? OK. So let's start with BERT. Well, we said we're going to get rid of this first part. We're not going to have any further requirement on producing a sequence. We are not going to produce words. Technically speaking, this is not even going to be a language model. It's going to take language as input, but it's not going to produce another output language sequence. We still want to represent stuff from the input as carefully as we can, and we'll see how to do that. We're going to rip away these decoders. We're going to just stack encoders. This is just a picture that we saw before, except instead of having a stack of encoders and then taking their outputs and plugging them into a decoder, another stack, it'll just be encoders. And you might say, OK, well, what's the point? All I'm doing is moving to this latent space. And the answer is, yeah, that's exactly what we're going to want to do. We are going to want to get good representations in the latent space. And then we can do stuff with them. We can build classifiers on top of them in a way that turns out to be very convenient and very powerful. OK, so this will be our BERT model. That is BERT over there. OK, so why is it called BERT? Well, partially because of this annoying Sesame Street name. So it follows Elmo, which is that character. We talked about Elmo embeddings way back. The story was the following. And again, this is what I talked about on the first day of class. Back in 2013-ish, people were trying to apply deep learning advances to language. And one thing they tried to do is to say, let's construct word vectors. Let's construct embeddings that carry the meaning of words, but in a static way, in a fixed way. Every word in our language gets one embedding, and that's it. And they had various ways of doing this, including some really powerful ones. This, by the way, is the website for the Project Glove, which is one of the 2 most popular kind of word embeddings. It's actually a very beautiful website. People should check this out. When you do a project, you guys should do something very similar to highlight the work rather than just write a paper. OK, so the downside is what we talked about. What is that issue? Anybody remember? Go for it. Yeah, so one issue basically is, well, we don't have any way of dynamically changing our representation based on the way the word is being used. And words are overloaded, right? They each mean different things in context. So if we ignore context, we're actually not going to really be able to know what's going on. OK, the example I keep using, although there's many others, is bank, right? It could be a building. It could be the side of the river. I don't know which one it is until I have a sentence to go with it. OK, then we talked about these contextual representations. These things use language model-like techniques, but basically what they do is they actually go ahead and include the context. So rather than having a lookup table where every word gets a fixed vector, I have a function. And this function, you put in the word, but you also put in the context. And depending on what that context is, you get a new representation for the word, taking the context into account. Does that make sense? OK, so that's an important thing to have, right? And you need a function there. It can't be a lookup table, because, of course, the number of different contexts for every word is huge. So you can never have a table that big. OK, so this was, for example, Elmo. This came out around 2017, 2018. And BERT came out very shortly afterwards. OK, so what's the difference between these two things? Not too much, right? Elmo was using LSTMs. That's sort of the previous state-of-the-art type of architecture for language. BERT came out once transformers had already been built. Again, that was 2017. So BERT used transformers instead and turned out to be more powerful than Elmo. Other than that, there's no huge difference here, potentially. All right, everybody OK with this? This is the little history lesson. Let's keep going. So BERT is the following acronym. B is bidirectional. We'll see what that means in 1 second. The remaining part is pretty clear, right? Encoder is the E, because as we said, we're going to stack encoders. R is for representations, same thing as embeddings, right? And finally, T is because we're using transformers. So it's an actual acronym. It has a meaning. The bidirectional part is the fact that we're passing in an entire sentence. And we're going to do full self-attention without any causal masking. So when we're building a representation for a word, we can look at the left side of it, but we can also look at the right side of it, right? Because it already exists. We're passing that context in. It's not one-directional, the way we have to have things in generative models. It has to be bidirectional here because we have access to everything. The context is all the surrounding part of the word. All right, everybody comfortable with that? And again, that's something that we actually already saw because that's what we were doing at the encoder for a transformer. It's nothing new. All right, let's try to understand what's going on in BERT. It's actually going to be very simple. As we said, we're going to take away all of our decoders. We're just going to stack encoders. And I'm going to make one basic change. It's not going to be really complex. At the beginning of a sentence that I pass in as input, I'm going to put in a very special token in that first position. This is called a CLS, or classification token. It's a fake token that we create for the purpose of this BERT model. It doesn't come from our real vocabulary of tokens. It's just a fake one. But there's a reason why we're doing this. Now, notice what happens, right? We're passing in our full sequence over here. There's some maximum length for what we can push in. This is just some sentence. Once again, I'm stealing it from the same guy who built this website. We pass it into our encoder layer. It's exactly what we know. We pass the outputs into the next encoder layer, and so forth. And what happens at the top? Well, we have a bunch of vectors, right? Now, we have a vector for every one of our input tokens, including a vector for this classification token. OK, so this vector that comes out the top for the classification token, we're going to train the model in a way that puts a lot of meaning into this token. Specifically, it kind of summarizes what's going on in that whole sentence. So we're going to have tokens for each, we're going to have vectors for each word at the output. But we're also going to have some kind of compressed overall representation. And that's going to be this very first vector corresponding to this classification token. Any questions about this part? Anybody confused on what we're going to be able to do with this? Let me give you a simple example. A very traditional NLP task is I give you a sentence, and I ask you, does this sentence have a positive meaning or a negative meaning? It's called sentiment analysis or sentiment classification. Now, when I try to figure this out, I have to look at the whole sentence, right? It's not enough to look at a single word. So somehow, I need some representation that compresses what's going on in the whole sentence. And then I need to take that representation and do something with it. Perhaps plug it into a linear model or something else simple. And that will go produce for us our output, which is yes, no, good, bad. Well, that's exactly what we can do with the vector that comes out of this first position corresponding to the CLS token, I can build something like a linear model on top that makes this prediction. So we can take that information and do stuff with it. It compresses everything that's happening in the whole sentence that we pass into BERT. All right, people look at least slightly confused, so ask me questions. Suppose you didn't have the CLS token, what would you do instead? Yes? Yeah, I could do that too. Yeah, all these things are reasonable. I could concatenate all the embeddings and pass them into a different layer. I could, for example, pool all the embeddings explicitly, take a weighted average or just an average, try to work on that. What's nice about BERT is that it doesn't force us to build these kinds of somewhat arbitrary things. It just tells us, hey, here's the information already. And it's trained in such a way that it knows it's supposed to do stuff there. All right, so let's see what these things look like. Pretty much exactly what we think for the base model, which was originally already kind of large, but by modern standards is pretty small. You're talking about 12 of these encoders. If you want to move to what was called BERT large, you have 24 of them stacked on top of each other. Nothing terribly special, and all these models are no longer super, super big. OK, so far architecturally, other than maybe adding in the special token, there hasn't been anything special compared to what we saw in transformers. The more interesting bit is getting into training. Now, training will be genuinely different from what we saw before. We are not going to have input-output sentences, because that's not what BERT is for. It's a foundation model. We have to find some fake tasks to train it on. Everybody agree with that? Yeah.
Will we have an end of time token or end of second?
Yes, we'll have a few special tokens that are not CLS. We'll have separator tokens that separate sentences. We'll have an end token, et cetera. And in fact, all of our language models are going to have a bunch of special tokens that we designed to help them. Great question. All right, so let's start talking about training. Now, we're going to do things in the foundation model way. We're going to pre-train. The pre-train will be on tasks that are not what we really care about. They're fake tasks, and they're self-supervised, which means I don't want to have someone come and say, this is the correct output. I want to be able to know it in advance from the data I already have. So we'll see two fake tasks that are actually very simple that we're going to use to train BERT. But when we actually want to go use BERT, we're not going to deploy it on the fake tasks. We're going to take our real tasks and fine-tune the base model to be good at those particular tasks. So pre-train, then fine-tune. This is the paradigm that we've talked about, and now we're actually going to be able to see it. OK, so let's talk about the two fake tasks that we're going to use for pre-training. Here's the first one. You can almost guess what it's going to be. It's called masked language modeling. It's nothing terribly shocking. We're going to introduce another one of our fake tokens that are not related to our language. It's going to be a mask token that we use in training. And what does this mask token do? It just replaces one of the input tokens. So it says, OK, instead of having a word there, put this mask thing on top. OK, now the model, when you're doing a forward pass, it does not know what the real word should have been over there in mask. That's fine. We let the model proceed. It goes up through the model. And then we have this vector that we have at the top. And we're going to now decode this vector. We're going to say, OK, well, what is this thing closest to? Very similar to what we did when we decoded to produce words in translation. And we're going to say, OK, well, that's going to be my predicted vector. And we're going to demand that our model can undo the mask and predict what was originally there. Now, where do we get that information? Well, we know it, right? We have all the original text before we masked anything. So we know what was supposed to be there. And we're just telling the model, hey, if I mask it, can you still predict what it's supposed to be? OK, everybody OK with this first task? Now, again, we're not going to actually deploy BERT to guess what words are in a sequence of words that we already know. That's not the point. We're just trying to teach it language. And we're saying, hey, if I give you enough context, you should know what a word should be. You should be very good at predicting that word. And if you can do this, then probably your representations are quite good. Yeah?
My question is just that, like, if we do that, so you mentioned that we'll still need a decoder in that case. What are the concerns that the decoder may have that information? What do we need to do to optimize the training such that the encoder learns the most information? While the decoder
Oh, sorry, I should have said it differently. I don't mean a decoder, I mean a predictor, right? I'm not going to attach decoder layers over here in the transformer sense. I just mean I'm going to take that vector, right? And I'm going to say, OK, well, what am I closest to out of all the word vectors that I have, right? That's all. Yeah? Not here, not yet, right? Over here, I'm not really doing anything actually with CLS. I'm not even going to mask it, right? All I'm doing is covering up words elsewhere in my sequence. And I'm saying, hey, your vectors that proceed from this mask should have enough information from the context to reproduce the original word. CLS is not doing anything yet. I see 2 more questions. Go for it.
How come the output is a whole sentence?
The output is one vector for every single token that we put in the beginning. So it's just a sequence of vectors themselves. And each of these vectors pertains to just one token. And now I'm saying, hey, from that vector, can I guess what the correct original word was? And I'm telling the model, hey, become good at doing that.
Okay, so in this case, it's still it's also a decoder out. There is no decoder.
Yep, yeah, no decoder layers here at all. From the top encoder, I'm just saying whatever vectors come out. And that's exactly what we had in our encoder stack in the transformer too. A bunch of vectors, one for each word. And I'm saying, hey, if my initial word somewhere was masked, is there still enough information to predict that original word? That's all. Okay. There's one more question? Yeah.
For the CLS token and the mask token, I mean, for the rest of the other words, there might be some embeddings. But what about the embeddings for CLS or mask? Because
So the embedding I'm getting from masking something is the thing I'm working on right now. I'm saying despite the fact that I put mask as a token there, I want the resulting embedding to still predict the word. Essentially, I'm forcing all the context to be sufficiently good to go ahead and predict what was originally there, despite the fact that I put this mask token on. Now, what I'm trying to do here in training is not to tell the model, hey, make sure that I get a vector that corresponds to the mask token. I want the opposite. I want a vector that comes out of the masked position that is the original word that I hid. Does that make sense? But you're right, the CLS token is not doing anything yet. So we still have to figure out something to help the CLS token know something about our sentences. And we're going to see that just now. We're going to build a second task. The second task is going to be a little bit different. It is not going to mask words and ask the model, hey, can you predict what those words were? It's going to say, hey, can you tell me if the next sentence here fits or doesn't fit? Now, this is another fake task, right? I'm creating a task where I have 2 sentences. And I'm basically saying, OK, does the second sentence make sense to follow up the first sentence? Now, how could I do this from a bunch of text? Well, I have text where there are already multiple sentences. I can take 2 consecutive sentences. Those fit. Or I can take 2 separate sentences that have nothing to do with each other, push those together. Those don't fit. So I have my ground truth already from my sentences. I know which ones are appropriate next sentences, which ones are not. And now I'm going to go ahead and demand that my classification token can be used to predict, yes, you got the next sentence right, or no, this shouldn't have been the next sentence. So it's no longer a word thing, and there's no masking involved. It's a thing where I'm using my classification position to say, hey, you should be able to predict that this next sentence makes sense, or it doesn't make sense here. And of course, you can kind of guess what this is useful for. Really, now the model has to be able to look at the whole input, everything that's in it, and try to figure out, does this kind of coherent, does this fit together, or not? And you have to be able to compress all that information into one thing for the classification tokens vector to be able to make that prediction. Cool. So 2 fake tasks. Both of them I can build based on just a bunch of text that I have lying around. Doesn't require any labeling, and it's not supervised learning. And these are meant to give you really good vectors and to be able to do this whole compression into the classification token position bit. Go for it.
Yeah, I was just wondering for this part, so you're saying that the way they measure the 2 sentences are like make sense to be next to each other. It's just that they read the entire sentence and then the output token could be a 0 or 1. 1 is if that fits. And 0
Yes.
if it doesn't. So my question is, during training itself, how do you construct the data set in order to recreate that data? Is it just like enumerating every possible outcome? That seems so expensive if you just like randomly mix 2 sentences together.
The latter, right?
Yeah.
So I have my input here is, let's say, all the text in Wikipedia.
Yeah.
There are many consecutive sentences in Wikipedia,
Yeah.
right? Those are your positives. Those are where the model's supposed to say, yes, this next sentence belongs here. And then I can construct negatives. I can take 1 sentence from here, 1 sentence from there. They don't fit together, right? So I can create data points of both types, class 1 and class 0. In neither case do I need to actually sit down and label points and say, hey, this is indeed the next sentence that makes sense or not. You see what I mean?
Yes.
Now, there's some complications. There might be some cases where I ripped a sentence from here and one from there, and therefore I say they don't fit together, but they actually did through chance. We're going to ignore that. Although it turns out in a lot of self-supervised learning, making that error can be a problem. Yeah?
So for these two tasks, we retrain on both the tasks simultaneously, or we select them?
On both, yeah. So both of these tasks, training on 2 of them, will give our model the capabilities that we want. Neither one by itself is really sufficient.
So like first we train on ML, then we train on.
Yes. There is a particular schedule that we actually use in practice, but yes.
So we use the weights from first train task.
Yep. So both tasks are part of training, right? So this is just basic multitask training. Both of these are hitting certain parameters, and you're updating the weights based on both of them. Cool, let's dig slightly into the first task, which is also usually the most interesting one. Okay, so for masked language modeling, the first question basically is how often should we mask, right? Where should we put these mask tokens? And which words should we mask? And again, if you don't do this the right way, then your model will sort of pay attention to things it shouldn't. So here's kind of the original choice that is made. And it turns out this is not necessarily exactly optimal. You can kind of change it a bit. So 15% of words at random. So I pick these words at random, and I decide, OK, that's where my mask token will go. OK, now here's something even more interesting that takes a little bit of thinking through. Of these 15% of words at random that we picked, 10% of the time we're actually not going to put the mask token in there at all. And you might say, well, why are we doing that? We decided to mask 15%. So why are we doing something different on some subset of those 15%? There are reasons for this. So we're going to say, OK, no mask, but do flip the word to some other word randomly. This is pretty interesting. We're basically injecting noise a little bit into our model. OK, and then 10% of the time, we are not going to do anything. We're going to keep things unchanged altogether, keep the original word there without masking. So this is pretty interesting. It takes a little bit of thinking through this. I suggest everyone spend 20 minutes coming up with potential reasons why we would like to do these things that don't make apparent sense at first glance. And then let's see if we can agree on them or not. You should be thinking of things like overfitting, the train test gap. One thing you could be thinking about is, will we ever see a mask token when we go use prediction, when we go to inference time? Anyway, spend a little bit of time thinking about this, because this is one of the most interesting design choices for BERT. And we'll talk about it next time and see if we can all agree on why this makes sense. But this is kind of the current schedule, not completely optimized, but these are the parameters that are used in actual training. And then finally, for pre-training, after we conclude pre-training, we'll do fine-tuning. And that's basically exactly kind of what you'd expect. Pick your favorite NLP task over here, and then let's go ahead and actually fine-tune for it. Right? So for example, squad is question answering. That's an old question answering data set that came from the mid-2010s. Right? So you're going to have here a question and a paragraph. You're going to try to figure out if the answer is a good answer. You're going to go ahead and predict that based on classification and so forth. You're going to look at the actual solution that you provided, which is at the end, and so forth. OK, so this is kind of the basic idea for BERT. Now, why was this a big deal? Well, basically, as soon as BERT was proposed, it immediately got state-of-the-art on all of these NLP tasks at once. And that's not very typical, right? Normally, if I introduce a new model, it might be better at task A and B, but not any better, or even worse at some other tasks. But BERT pretty much immediately set state-of-the-art in everything you'd like. And the other cool thing is it's very scalable. You can just get a bigger version of BERT that performs even better. So this is the basic idea. We built this foundation model. We did the things that we've been talking about: multitask training, fake pretext tasks for pre-training. And then we finally said, OK, let's fine-tune it to produce whatever it is that we want. And in fact, we actually could use this guy as a language model. It's not completely impossible to do that. I could do things like, let's put some mask tokens in, and then one by one have BERT spit out what those should be. It'll turn out there's other models that we really prefer to use for that. But theoretically, you could adapt BERT to be a language model as well. OK, so that's the story. This is our first foundation model, built on transformers, yes, but kind of in the conventional sense of a foundation model that's pre-trained and then fine-tuned on the things that we care about. OK, let's take a break. We can spend 2-3 more minutes asking questions, and then we can move on to the other type of model that we want to talk about, decoder only. All right, I'll come here and then, yeah.
That's the magical part about the mask. What we're saying when we're masking a word is we're saying, hey, there should be enough context surrounding you that influences your embedding in such a way that you still actually have a very powerful embedding for this word, right? It's giving you that contextual information. Now, when we go deploy, we're not going to put a mask on that word, right? We're going to show it to the model, and then we're going to get the embedding that we want from it. And this is going to contain all the information in context. Now, of course, sometimes we don't care about just getting the word embedding. We care about doing some other NLP task. And that could be at the sentence level, so we use the class domain. Or we might make a prediction. We might use a mass domain analysis, for example. You see what I mean? Does that answer your question?
Like, if we have to do those
Yeah, exactly. Exactly. Yeah.
that's hard. But when we like mask some of the tokens, now, okay, then that is the output sequence, but we actually use a decoder to generate words, right? How would we have to use it?
We're not going to use a decoder in the sense of a layer, right? So we're not going to take and push in a whole new layer like we did. All we're going to say is that we produces that. Right? We can, and I use the word decoder, well, an overload over here. We can take a vector, and we can figure out, hey, what does this represent? For example, what is the closest embedding in the vocabulary for this guy, right? I can go ahead and make a prediction for what word this vector was supposed to represent. That's what we're doing. We're saying, hey, did you get the right word when I covered that?
What is the embedding of that word? Like, for example, if you ask
Being trained during all. So all that's being trained and with the model.
So, for example, we might see what we get some word answers embedded. How we know that this is correct embedding, where we have that exact mapping of the C.
We are going to have an embedding layer. It's the same that the input. And these embedding layers are trained. So nothing special happens. Same as before, basically. The way to think about this is take that decoder, the last decoder on the transformer. Except we're going to remove this decoder. No problem. But take that predicted one, right? Where we go and say, hey, I can now say this vector represents this token. So that's the thing we're trying to do. But notice that this thing, just doing that doesn't train our classification token, so we have to do other stuff for it. Yeah, exactly. Yeah. Yes. This was fixed. In practice, we could do other things with that. We could make it longer. We could say, hey, we can go ahead and like map these words. Just add them. So it's not up to us. I've told this with convenience. These models are just get that easy. We can have a special token tool that says this is the end of our deployment and thank you. What's the other question? Yeah. You're not going to retrain that, right? You're going to say based on your skip that. Download this retrain version. Large model, you download that one. And then go ahead. Or the yes, well, you may not need this, right? But for example, two things I think I mentioned. Makes sense. I just take my whole sentence and try to make it predict correctly off of the sentence. And I might have one predictor with the correct labels off of the Now, of course, you get more fancy. There's lots of tasks you could do this for, depending on how creative you get. So you're not really repeating the original two. Yeah.
I have a quick question. I was wondering why, so in the pre-training step, we kind of mask
part of training. So you're seeing some randomly masked here, this one and this one. You have to predict the correct one. That's part of pre-training. The only other part of pre-training is this guy, next sentence prediction. That means using the embedding initiative here to predict whether the second sentence is appropriate for following. You train on those two things, which means looking at this guy, this guy, this guy, or other masked words are
Why do you want this?
Do you want to I want to understand very well what's in my input sentences. That's sort of the second test area. I just want to be able to have a lot of contextual about what's going on in each word's representation. Say if I said to just use the context, did you learn anything else you need to know what's original? That's pretty much it. Of course, we can make other ways to make it. Very possible. There's no easy way to get rid of it. Yeah. Yes, because you're not really going to, first, the amount of data is much, much smaller. And two, we're not going to really talk about it later, but I'm continuous. I may change only some layers instead of the whole thing. But however, notice that things like Laura and other more parameter fine-tuning methods didn't exist yet. So that's not showing up in like traditional print.
So what is the
I know there's stuff about different ways of trying it. I don't know if there's anything just better than random way to do it, right? Compared to yeah.
There can be some other.
There's definitely cool studies, but I don't know it. So let me check on what's actually.
Yeah, it's a thing. It might be.
Yeah, that's quite interesting. Okay, let me read the scene and look at that. Okay.
But for pre-training the
Yes. So I mean, pre-training, of course, you get some measure of that's not because I don't care, right? Like the pre-training tasks weren't useful just because you get very good at them. Everything is about how you
Just a quick question. So we do have other when it comes to
For example, you can say, hey, I mean, just go ahead and push it into the class token, but we would do that if we do something with examples and fine-tuning. So the model learns, yeah, it's supposed to do that extraction, that's what the result is there, right?
okay, it learn it on the way.
Yourself to perform. Yes. We're forcing the model to make the correct prediction doing something like that.
CLS for the first sentence will give me some summary.
No. I put both sentences in at the same time. I put a separator another special token that tells you, okay, first sentence is the second sentence. Okay, now the model's supposed to figure out that these two separated sentences, the second one fits the first one. And it's going to put that information into the vector that's coming from the CLS token at the beginning. And that information is the vector. And then I'm going to have a layer that projects it with prediction 0. Same as we do with binary classification or any
CLS is basically
yeah. But later we'll use it for any kind of prediction. Whatever kind of task we have that involves looking at the whole sentence and making a prediction, we're going to use it for that. But we have to find it. It doesn't know that in advance. All right, so we had tons of good questions, and as a result, we are almost exactly out of time. Let's spend 1 minute going through quickly. So we're going to talk about this more next time, but the GPT model is what we do if we do the opposite. Instead of a bunch of encoders, let's do a bunch of decoders. We no longer care about the second part, which is getting a lot of preservation of the original sentence. We now just want to have natural language outputs that follow from whatever thing came in the beginning. So let's rip away our encoders, stack decoders. This is exactly what GPT is.
here's a bunch of examples for different model sizes for GPT-2, which is actually small enough that you can kind of reproduce it on your own if you can afford, $50 worth of GPU time on a server. OK, so won't spend too much time on this till next time. But again, it's not too different. The only thing that's different from the transformers architecture is notice that we're going to have masked self-attention over here. We don't know the future, right? Just like before. So we have to go ahead and make sure that in our self-attention layer, this stuff is masked out. OK, we'll talk more about this next time. But exactly what kind of attention mask to use is actually a pretty interesting question. There's other variants that do other things than just kind of mask out the future. Let's spend our next lecture talking about this stuff. We'll stop there. You folks have a good weekend. And please check out homework 1 when it comes out tonight.
Very interesting. Recently built it on top of the SSM set. It's like I have well, that's a popular research. Yeah, right. For that. Paper that I that first paper was literally just saying adding to the kernel that works.
Yeah, I mean, there's a lot of people did this back then, but they didn't have enough scale. They didn't have enough tricks, right? It didn't work well. It's a state in transition matrix, right? So this is the part that we should be especially careful about. There is a state variable, that's the x. That's where the state is stored. A is the thing that says you should transition. So A times x is like what happens to get the next. Now, okay, so what should be in A? Because it's a great question. So the answer is I want to extract the most relevant stuff about the past, right? And then sort of keep it somewhere and give enough space, basically, for more information. That's the intuition, but I have to translate something mathematical. Okay, and now it's going to turn out that this is very closely related to something coming from like very advanced algebra. It comes from something that is called orthogonal polynomials. Essentially, you can represent a lot of information in a special basis of functions. Somehow, if I pick the right basis, I'll forget the very least information I can, and then I can encode this basis into A. But there's a lot of fancy math to get there, so if you get into it, you should read the paper. It has these details, like they construct A in a very, very special way. And if you don't build A in that way, things are much worse, right? You forget much more often. But yes, if you do decide to read the paper, there's a bunch of extra resources that can help, and I can help you out with those as well. So come talk to me in office hours or something. We can chat about it. This afternoon, yeah. Oh yeah, it's a huge space. Yeah, so I mean, there's 2 or 3 kinds of results. So the first thing that people often do is just say, okay, what kind of things can a transformer express? Forget training. If I'm allowed to pick out the weights arbitrarily, can I do this? Or can I do it with this number of layers or this width, right? So these are representation results. Can transformers represent a function of these properties if I have X, Y, Z resources for a transformer? There's a ton of results like that. Then there's a bunch of results around, well, training itself, right? How do I know that if I train on some data, I'll get some performance? This is very hard. We don't even know good theoretical results for training a very basic, MLP with 3 layers, let's say, on a simple task. Like, this is still unsolved largely. But, training on a 1-layer, let's say, linear transformer, there are results like that, just as an example. Finally, there's all kinds of stuff about, let me pick very special, super abstract tasks, like a binary counter, right? 0, 1, 0, 1, right? Like, can I show and prove that a transformer can learn that if I fix some stuff? Yeah, very, very simple ones. But we hope to have a good theory for 10, super abstract simple tasks that we can build up on or whatever. Yes. Yeah. Yeah, and there's a very beautiful paper about so-called shortcuts. So transformers can look at the training set, and figure out not really the underlying mechanism that you can use for prediction, but some way of guessing the correct answer based on like memorizing certain patterns. And then when we show them new versions, of course they token fit, right? There's some actually very nice theory about when this happens. Yeah, if you're interested, I can share a bunch of these papers. You could take a look at them or try to read through them. But yeah, the field is still early, right? We don't have good theory. Longer than 512? No, unless I, compress that information through pre-processing. I could, yeah, I could try it. But unfortunately, there are going to be some other effects that might kill you from doing this. Like, can you push in a longer number of tokens? Yes. Will that be compatible with what happens with pre-training? I'm not sure if it is. That's the connection. For the reason you said, you can do it, right? Like, there's nothing inherently stopping you from it. But I think it might break. But I can't prove it, so I'm curious if someone's tried this. It's probably, there should be some literature out there on like long context BERT or things like that.
Because let's say BERT is pre-trained, right? We already have downloaded the BERT model.
Yeah.
Now we have bigger tasks where
Yeah, I get what you're saying. Well, if you fine tune, yes, you should be able to do stuff like that. Now, how long can you handle? You have the computational complexity problem still, right? So that's still an issue.
but like is there any other method?
Oh, that's what you do, right? There's a bunch of tricks as well. Like you could do things like change the attention mechanism. You can make it approximate instead of having full attention, right? And that gets you the complexity that you want. And then there's the kind of training tricks that let you do longer sequences than what you started with initially. Yeah, I guess the more I think about it, maybe it really is possible. People don't typically do that because there's less interest in can I compress extremely long sequences with BERT typically.
Like if I have 1,000 tokens of sentences, like I have data set, so like I want to classify this like sentence analysis and data set where we have thousands.
Well, if you really want the boring answer, I mean, it is, I'm not even going to use BERT. I'm going to do classification with a generative model instead. And where people have solved the problem, well, partially solved the problem of very long context ranges. So that's the answer. But I think everything you're suggesting could be done for BERT. Like nothing sounds impossible there.
But the accuracy won't be as good as generative.
There has to be some cost, right, somewhere.
Okay.
Now, if you said, hey, if I'm going to scale up BERT to the length of a typical massive generative model, maybe it's better, right? Like, that's another good question. I don't think anyone's tried, 1 trillion parameter version of BERT, for example. Although that'd be also very interesting to see. Yeah, interesting question, though, honestly. Hey.
I was wondering about